For 40 years, astronomers were staring directly at the brightest object in the universe, and they didn't realize it. They thought it was just a star. But in 2024, scientists discovered the truth. That star is actually a quasar 12 billion light-years away, and it shines with the power of 500 trillion suns, the brightest object ever discovered. Which raises an obvious question. How could something this bright hide in the sky for 4 decades? Why didn't anyone notice? But the real mystery is even stranger, because the object itself is not the biggest problem. Across the universe, astronomers are finding black holes that formed when the universe was still a cosmic infant. Some appeared less than 500 million years after the Big Bang, and according to our current theories, that should be impossible. Somehow, the early universe was creating monsters far faster than physics says it should. Black holes billions of times the mass of the sun, appearing almost overnight in cosmic history. So how did they grow so fast? Where did they come from? And could the answer mean we fundamentally misunderstand how the universe built its most powerful objects? The object is known as J0529-4351. It was first cataloged in 1980 during sky surveys searching for distant quasars, but nothing about it looked unusual. It appeared as a simple point of light, exactly what a distant star should look like. So it was quietly filed away in star catalogs for decades. The reason is surprisingly simple. Modern sky surveys rely heavily on automated classification algorithms. These algorithms compare the color and brightness of objects to known patterns, and J0529-4351 looked too bright to be a distant quasar. Statistically, the algorithm concluded the only reasonable explanation was that it must be a star inside the Milky Way. But when astronomers reanalyzed the data with more advanced techniques, something strange appeared. Its brightness was fluctuating, not slowly like variable stars, but chaotically, violently. That kind of variability is a signature of quasars, so astronomers pointed larger telescopes at it and examined its spectrum, and the result was unmistakable. The light from J0529-4351 had been stretched by the expansion of the universe. Its redshift placed it 12 billion light-years away, meaning we see it as it existed when the universe was less than 2 billion years old. And yet somehow, it is brighter than almost every other object ever discovered. Which leads to an obvious question. What kind of engine could possibly produce that much energy? At the center of J0529-4351 lies a supermassive black hole. Its mass is estimated at 17 billion times the mass of the Sun. But the mass alone isn't what makes it extraordinary. The real shock is its feeding rate. This black hole is currently consuming matter at a rate equivalent to 1 sun every single day. To visualize that scale, imagine our own sun being torn apart and swallowed whole, a cataclysm that repeats itself every 24 hours without end. In theory, black holes cannot feed arbitrarily fast. A physical limit known as the Eddington limit acts as a natural speed limit. When matter falls toward a black hole, it heats up and emits radiation. If the feeding rate becomes too high, the radiation pressure pushes gas away. The black hole effectively chokes on its own brightness. But J0529-4351 is feeding extremely close to that theoretical limit, as if it is pushing the laws of physics to their maximum allowed intensity. And that feeding process creates something enormous. Before the gas disappears into the black hole, it forms a gigantic rotating structure, an accretion disk. The accretion disk around J0529-4351 is not small. It stretches roughly 7 light-years across. To visualize that distance, consider the orbit of Neptune. Now expand that distance 15,000 times larger. That is the scale of the glowing disk surrounding this black hole. Inside the disk, gas spirals inward at incredible speeds. Friction heats the material to tens of thousands of degrees. atoms are ionized, magnetic fields twist the plasma into violent storms. The disk becomes a furnace of ultraviolet and X-ray radiation, and the result is a beam of light so powerful that it outshines entire galaxies. But strangely, J0529-4351 is not the biggest problem facing astronomers, because quasars much earlier in the universe pose an even deeper mystery, and they should not exist at all. To see why, we have to look further back in time. For years, the earliest known quasar was J0313-18. We observe it only 670 million years after the Big Bang. Inside it sits a black hole with a mass of 1.6 billion suns. Even that discovery was difficult to explain. Growing a black hole that massive in such a short time pushes standard models to their limits. But new discoveries made with the James Webb Telescope and the Chandra X-ray Observatory revealed something even more surprising: a quasar known as UHZ1. We see it as it existed only 470 million years after the Big Bang. The universe was barely 3% of its current age, and yet a supermassive black hole had already formed, which creates a severe problem for astrophysics, because according to our best models, there simply hasn't been enough time. The standard theory begins with stellar black holes. When massive stars die, they collapse into black holes with perhaps 10 or 20 times the mass of the Sun. Over billions of years, these black holes merge and gradually grow larger. But UHZ1 breaks that timeline. Even if its black hole had been feeding continuously at the Eddington limit since the very first stars formed, it still should not have reached its observed size. And the mystery becomes even stranger when we examine its host galaxy. In most galaxies today, the central black hole represents roughly 0.1% of the galaxy's mass. But in UHZ1, the black hole may account for 10 to 50% of the galaxy's total mass. It outweighs its own galaxy, which suggests a radical possibility. Perhaps the earliest black holes did not begin as stars at all. Astronomers now suspect a completely different origin. In the early universe, enormous clouds of pristine hydrogen gas existed before stars formed. If one of those clouds collapsed rapidly enough, it might skip star formation entirely. Instead of becoming a star first, the entire cloud could collapse directly into a black hole. These are known as direct collapse black holes. They could start life already tens of thousands of times more massive than the Sun, giving them a massive head start in the race to become supermassive. But even this explanation may not solve the entire puzzle, because when astronomers examined the environments around some of these ancient quasars, they discovered something deeply strange. To grow rapidly, black holes should live in dense environments, galaxies colliding, gas flowing inward, plenty of material to consume. But observations with the James Webb Telescope revealed something unexpected. Many early quasars appear to be isolated, not surrounded by dense clusters of galaxies, but sitting in relatively empty regions of space, which means the supply of fuel should be extremely limited. And yet, these quasars shine with the power of trillions of suns. So where is the fuel coming from? One possible answer lies in the large-scale structure of the universe. Across billions of light years, dark matter forms a vast network known as the cosmic web. Galaxies form along these filaments, and along these filaments, enormous streams of cold hydrogen gas may flow through intergalactic space. Instead of heating up and forming stars, these rivers of gas could plunge directly toward the galactic center, feeding the black hole continuously, like a gigantic cosmic straw delivering fuel straight into the monster. But the story doesn't end with feeding, because quasars don't just consume matter, they attack galaxies. As gas spirals toward the black hole, enormous amounts of energy is released. Radiation floods the galaxy. Powerful winds erupt from the accretion disk. Some of these outflows race outward at thousands of kilometers per second. When they collide with the surrounding gas, shock waves ripple through the galaxy. Cold molecular clouds begin to break apart. Star-forming regions are torn into pieces. And as the quasar grows brighter, the winds grow stronger. Eventually, they become powerful enough to push gas completely out of the galaxy. Vast bubbles of gas are blasted into the void, depriving it of its lifeblood. Deprived of its raw materials, the galaxy begins to suffocate. The factory of star formation simply shuts down. What remains is a cosmic tomb, a silent expanse of aging stars drifting through the dark. This is not destruction by collision or gravity. It is a quiet, internal execution. The very monsters that anchored these galaxies grew so violently that they extinguished their future forever. And that all began with a point of light that astronomers once dismissed as an ordinary star. But that star turned out to be one of the most powerful objects in the universe.